Welcome back to our video module on quantum mechanics. Today we're going to be looking at spherical Bessel functions, especially how they relate to solutions in quantum mechanics. Now, as a quick refresher of the roadmap that we've taken, we started off with some sort of wave function. It was a function of r, theta, and phi. And what we found is that there's some quantum numbers associated with that, n, l, and m. We were able to separate that into two functions. One was a radial function and the other was a spherical function, which basically looked at theta and phi in polar coordinates. Now we've taken a look at this pretty carefully and we're able to find some solutions that gave a feel for what the probability distributions looked like. In order to get to our next step, we're going to assume a certain potential profile, basically the infinite spherical well, where v equals 0, where r is less than a, and v equals infinity, where r is greater than a, basically reflecting our first one-dimensional case of an infinite square well. And using the separable approach with the infinite spherical well potential, along with a number of variable substitutions to make the math of it easier, we've come to this equation right here. Now, the first thing we might do is we might say, well, okay, let's make L equal to 0, which means this whole term goes to 0. We're left with a negative k squared u, which means we're going to have some u that's of the form a sine of x. However, we need to remember that u was a substitution for the real variable that we're looking for, and that's uppercase R. And in this case, if we say L equals 0, and let's go ahead and write that right here, L equals 0, then we know that R as a function of R is, you can go through the math and do this, but sine of n pi r over a all over r. And those of you who are pretty savvy know that this is going to be of the form of a sinc function. And I've gone ahead and graphed that, and let's pull that up here. And this is a symmetrical showing positive and negative x. Of course, we'd only be looking at the left or the right-hand side over here. So this gives us a basic feel of the probability density as a function of radius for L equals 0. In other words, there's no angular momentum component in 3 dimensions, and you can see that really the bulk of what we're looking for is right here at 0, and then it decreases rapidly as we move away from the origin. Now this is where things start to get pretty interesting. Now what I've done here is I'm drawing something that looks basically like an infinite square well, and you can imagine that if it really were a 1D infinite square well, recall you have your first solution, and then maybe up here we'll do a second solution where we have 0 nodes, 1 node, and then maybe up here 2 nodes. And by applying boundary conditions, we're able to take a sinusoidal function and compress it or expand it so we have the right number of nodes. And in fact, this is precisely what we're going to do here. Instead of seeing this well as a 1D well, we're going to see this as simply a well looking at the radius, just a radial component, remembering that theta and phi don't even come into play in finding solutions when we're looking at just R, as long as we have a radially symmetric potential profile. So what that means is, let's take a look at what we expect our first solution to be. Our first solution is going to follow the sinc function right here, and we expect no nodes. So that might be something that looks like this. One can imagine, well, what would it look like if we were to have now 1 node? Now I'm going to make the heights a little different because once we bring in normalization, that's going to affect our values. Here in red, we see what it would look like at a higher energy where we have now 1 node. You can see what the next one would be. You can guess that 2 nodes would probably be, a little higher, and we're going to come down and here and here. And basically what we're doing is we're following this graph until we get to our 2 nodes finished. And this way we can get increased energies that follow this particular graphical profile and still not violate any boundary conditions. So this is a great approach for looking at and making sense of possible solutions for L equals 0. And of course, you'd be asking, well, okay, I see where the orange one comes from, where we look at our first solution, but where do we get these other solutions? And we get them from the same place we got them on the infinite square well. We get them as increased energy. As energy increases, we have more nodes. So let's move things around a little bit. We've taken a look at the L equals 0 case, and we'll keep that up in the top right. And if we introduce non-zero L's in this equation, we end up with something that looks like you are, and I won't get into why this is the solution. We want to play with the solution today, not derive it. We basically end up with some J of L of KR, where this right here is a spherical Bessel function. We're not going to get into the Neuman function solutions because they don't really mean anything in quantum mechanics right now. From here, we can create an equation for the actual radius, which is AJLKR. And just for kicks, why don't I write down what that spherical Bessel function actually is? You'll notice it's a function of L in the exponents, which really are both exponents and orders of derivatives. Now, just for kicks, I've gone ahead and graphed the spherical Bessel function for 3 L's. L equals 0, L equals 1, L equals 2. Now, if we're lucky, the spherical Bessel function for L equals 0 should look exactly like what we saw earlier. It should be a sinc function. And in fact, check out the red. The red is the only one where you have a non-zero number at 0 in the vertical axis, and it in fact is a sinc function. It's exactly what we found earlier. What's interesting now is that let's take a look at the green one. The green one, this is for L equals 1. And once again, if we were to play with this and try to understand what's happening from a spherical perspective, we could look at this as radial bound solutions. The lowest energy is going to have the least curvature. Same ideas as the infinite square well, where n equals 0 is 0 nodes, n equals 1 is 1 node, where you're increasing the energy now. And what we would see is that in the green, at n equals 1, we continue to this point right here. And of course, the heights are going to be a little bit different because of normalization. And likewise, if we were to increase our energy to 2 nodes, we're now looking at the green graph all the way to here. So you can see that the Bessel function provides a basic shape or profile of our final solution. The energy tells us how many nodes, how much of that solution will we, quote unquote, compress or put into this model to meet the boundary conditions. And finally, just for kicks, in yellow, let's go ahead and do L equals 2. And what we see is something kind of interesting happening that we're going to try and make sense of when we look at the blue line over here. When we look at the blue line, notice it doesn't go straight up, but rather it goes along 0 for a little bit. It kind of like it wants to get away from 0, and then it goes into normal cyclical behavior. And if we were to take a look at what stationary waves might look like, you can see n equals 0 in orange with 0 nodes, and in red n equals 1 with 1 node. But notice that around 0 it's kind of pushed away, and we might expect something like that because as L increases, that's a placeholder for an angular momentum concept. As we're increasing L, we're increasing our angular momentum. That's going to mean that the probability of our wave being close to 0 is going to become increasingly less. And in fact, if you look at, just for a moment, let's pull up the spherical Bessel function for L equals 10, and you can see that none of the solutions want to be near to 0. So for instance, take a look at this dark blue that goes right here. You can see that's your quote unquote ground state. That's your minimum energy state. And almost all of it is way off to the right. It wants nothing to do with locations near the origin. Finally, I'd like to introduce one graph that you'll often see as an expression for spherical solutions. Here we're taking a look at L equals 10, and what we've done here is we've said, okay, well, this is the solution where there's only one node. Here is the solution where there are two nodes. Here, the solution where there's three nodes, and it allows you to see that vertically, these things are the exact same shape. Now, normalization might change the height, but the idea is here we're just looking at increasing the nodes or decreasing the nodes, whichever way you look at it, of the spherical Bessel function. So in summary, what we've looked at is we found various solutions of the separable radial component of the wave function in 3 dimensions. We've seen that there's this heavy angular momentum dependency of L, that when L equals 0, we have a nice sinc function, which is what we'd expect. But then when we look at larger values like L is 1 or 2, or in this case, over here we had 10, we're able to use the spherical Bessel function to identify specific solutions. We also finally saw that increasing the energy, which means increasing n, in any of these situations is going to increase our node, which will allow us to kind of look further down the spherical Bessel function and still meet our boundary conditions. I hope this has given you a conceptual feel of the spherical Bessel function, how to use it, and how it fits in our broader exploration of 3D quantum mechanics.